Hey guys, welcome back. This is the fourth tutorial in our MCP series. Today I'm going to show you how to build your own MCP client. You've probably seen plenty of videos on building MCP servers on YouTube, but hardly anyone talks about the client side, even though it's just as important. That's why we are here. You can use tools like Claude Desktop or your local IDE to connect to an MCP server, but as you get more serious about automating your workflow with AI, you will realize you need your own custom UI. Why? Because you know your workflow best, and off-the-shelf tools already let you customize the interface to fit your needs. Another big benefit is with your own MCP client, you are not locked into any specific language model. Use whatever LLMs you want. Design your own prompts and tailor your AI agent for your use cases. That's what we are covering today. Let's dive in. Let me take you through what the MCP client can do. When it comes to connecting to remote MCP servers, you've got three options. Option 1, build your own self-host MCP server. Check out the previous video with the link below where I walk you through building one with a faster MCP. Option 2, use an official remote MCP server. Some services like GitHub already provide their own MCP servers. If your provider has one, you can connect directly with your personal access token. Option 3 is leverage an MCP orchestration platform. Platforms like Composio let you manage and connect to multiple MCP servers easily. Once you've set up your server, hit the test connection to make sure everything is working. If it's successful, you will see a list of available actions. These are the MCP tools you can use. For example, if your connection to a GitHub MCP server has 67 tools, you will see them here, and you probably don't need all of them, so you can pick and choose which one you want to use. The last panel is the tools interface. Here you can manually trigger a tool or just chat with the AI on the left to get the job done. The UI is intentionally simple and clean. Yes, there's a dark mode and light mode toggle on the top right. The best part is fully extendable. You can add as many MCP servers as you want, customize the UI, or even build your own prompt libraries. Want to add custom workflows? Just go for it. In this tutorial, I will show you how to build this client app from scratch in less than an hour. We will cover the initial Next.js 15 project setup, in-depth explanation on how the MCP client works, system prompts that I use, Vercel AI SDK, and how to set up your remote MCP server with Composio. Let's go. Alright, let's get our hands dirty. First, we will spin up a new Next.js 15 project. Open up your terminal and run npx create next app. We'll ask you the project name, or just type in MCP Client Tutorial. It will ask you a series of prompts. TypeScript, yes. Linked, yes. Tailwind CSS, yes. Just go with the default options for the remaining questions. After installing the dependency packages, we can seed it into the project folder. Now, before we write a single line of code, let's talk about context engineering. Think of it as setting up the stage for your AI assistant, like Copilot, to actually help you, not just spit out the random code. AI is only as good as the instructions and context you give it. That's why we are going to set up a solid folder structure for our prompts right from the start. Here's how I like to do it. Create a folder called .github at the root of your project. Inside the .github, add a file named copilotinstructions.md. This is your prompt orchestrator. It tells your AI assistant how to behave and what context to use. Next, create a prompts folder inside the .github. This is where you will keep all your detailed task-specific prompts. For example, prd.prompt.md for your project requirements. UI.prompt.md for UI-specific instructions. Why split them up? because LLMs still have limitation on the context window. If you dump everything in at once, you will hit that limit very fast before AI starts doing any coding. By modularizing your prompts, you can feed the AI only what it needs for the task. Alright, for the structure is sorted. Next up, we will start writing the actual prompts. Let's start with copilot instructions.md file. This is your prompt orchestrator. It sets the ground rules for your AI assistant and gets read in every conversation with AI. The trick here is to keep it short and simple. If it's too long, you will waste context window space. Here's my approach. I always go with a role play. So I will kick things off by telling the AI something like, you are a full-stack AI developer experienced in JavaScript, TypeScript, MCP Server, Client, and Vercel AI SDK. Next, I will spell out its mission. Your job is to manage and implement a custom MCP client interface that integrates with the remote MCP servers and the Vercel AI SDK. It will do this by reading and following a series of instruction prompts. Then I tell the AI where to find the detailed prompts. PRD prompt is for the project requirements and objectives. Architecture prompt for understanding the MCP client architecture, integration details, and dependencies. The UI design prompt is for UI requirements, component specs, and styling. I also include a few high-level coding practices. For example, to use TypeScript, write comments and docs in Australian English, plan before coding, and commit after each task. And when it commits, it needs to use the conventional commit messages. The prd.prompt.md file is even simpler. Just tell the AI what you're building and the key requirements. There are functional requirements. For example, it needs to be a web-based MCP client with the integration to the remote MCP servers, etc. There's also non-functional requirements. For example, it needs to be responsive and needs to include the dark and light mode support. Just keep it short and clear and straight to the point. Now let's look at the architecture prompt, which is one of the most detailed prompt files that we have. And at the start, we will just make some key architectural decisions. There's no persistent connections, so each MCP operation, for example, test connection, call tool or list tools, etc., will create a brand new connection, performs the action, then disconnects. For the configuration management, all the MCP server configs, for example, the URL, bearer token, they are stored in the local storage. There's no server-side section management. When it comes to the folder structure, we have the app folder as part of the Next.js app router setup. Under the app folder, we also have the actions folder, which is for server-side actions. We put the type definitions under the types folder, and we have the utils folder to host the client-side hooks, utility functions, and storage management files that we need for local storage. In parallel with the app folder, we have components folder, which hosts our UI components. Some code snippet to show AI how to create a MCP operation. You have the connection and disconnection as part of each connection cycle. When it comes to the AI chat system, it's relatively complicated. And we just need to show the AI how he should manage the data flow. It initiated from the user input, and the message will type into the chat panel. When the chat is submitted, it will trigger a use chat hook at the client side. But the actual stuff is happening at the server side. So whether it's MCP connection or the LLM call, it always happens at the server side. What's in the client side is just a use chat hook that triggers the server side actions. Then the message will go to the AI provider. And in response, it will get the string response back from the LLM provider. And then we update the UI accordingly. Some provider configuration. In this example, we picked AWS Bedrock and Google AI Studio, but you can also use OpenAI and any other LLM providers. We also tell the AI how to manage the tool permissions and execution. Here's again a tool execution flow for the AI to follow and understand. Here's a detailed event chain when it comes to the tool execution toggling and how it gets included in the LLM chat. Again, there's a detailed flow just in case AI will misunderstood, and it's just to facilitate the code implementation and give a very specific instructions to the AI. In summary, it's a stateless design which we use to build a reliable MCP client, AI chat with the real-time tool integrations and permission management system, and there's the immediate UI updates via the custom local storage events, which keep the UI and our local storage in sync. The last prompt file is our UI prompt. So it's just a simple file to tell the AI the key UI components that we have. So it will need to have a header on the top, displaying the title of the application, and that's where we have the dark and light mode toggle. Then under the headers component, we have the resizable containers. So the resizable container will host both the LLM chat panel and the MCP control panel. Inside the LLM chat panel, there's also subcomponents associated with the LLM chat. In MCP control panel, we have a list of subcomponents, which includes info panel, MCP control panel header, and also the server configuration components, available action components, and the last one is the tool interface. We also specify the CSS framework. We use Tailwind CSS, shadcn UI as our UI component library. Here's our color palette. You don't need to use exactly the same color palette that I used, but yeah, just some standard ones to start with that covers both the light mode and dark mode. All right, let's kick off our actual building process. I always start with the UI components. That's what I normally do in a full stack project when coding with AI. We will focus on the UI first and leave the API calls and the backend integrations for later. This keeps things simple and let us see progress quickly. Here's what I tell the AI coding agent. Please read the architecture and UI prompt documents we created earlier and start planning the UI implementation. Just build the UI components first and don't worry about API calls or the backend integrations yet. The AI starts by reading the prompt orchestrator copilot instructions.md by default. It also reads architecture.prompt.md and ui.prompt.md because we've set up the context in Copilot instructions to point to those files for more details when it needs to. Next, the AI begins installing dependency packages. I made a small mistake here. I told the AI to install the Vercel AI library, but in npm, the package is actually called AI. Luckily, Copilot figured this out and installed the correct libraries for me, along with other necessary dependencies like Lucy React, Tailwind Merge, and so on. Now, it's creating the components as per our instructions. We've got components folder alongside the app folder. Under components, it creates the UI folder and also sets up the lib, types, utils, and actions folder as specified in our prompt instructions. Once all the main UI components are created, the AI agents start editing global.css to set up the main CSS configurations with Tailwind. Sometimes it asks me to confirm if I want to continue properly, a cost-saving measure from Copilot, just in case someone has abandoned the section but the Claude model is still burning the compute. Next, it prompts me to install Redux UI libraries. You can just click through these pop-ups, then it begins creating basic UI components like Calypso and Separator. It also asks if I want to install the Next theme package, which is used for toggling between light and dark mode, as specified in our instructions. After that, it requests to install the React resizable panel. This is a resizable container I mentioned in the prompt. It separates the LLM chat panel from the MCP configuration panel, so you end up with two panels sit side by side. Now, it looks like most of the work is done. The AI asked me to run npm run dev to spin up the dev server. Let's check it out. As expected, the UI isn't the fanciest or most lovable you have ever seen. It's very basic, but well, all the functional requirements are there. Light mode, dark mode, toggle, MCP control panel, tool interface, Calypso buttons. It's not the prettiest, but well, that's okay. We can fix that soon. Before moving on, don't forget to commit your code. Add the newly created files and commit them to your Git tree, following a normal workflow. This keeps things tidy before we polish up the UI. Now, let's move on to the next step, polishing our UI. We are not ready to sell this UI to anyone. So I just tell the AI agent that the UI needs a bit of work. Since I've already created a polished version, I can just take a screenshot and ask the AI to replicate the exact layout I made before. If it's your first time building a product or MVP, the best way is to visit some UI showcase sites. For example, Dribble. Grab a screenshot of the layout you like and use it as a prompt for the AI to follow. Also, I need to be more specific about using the right library. I don't think the AI strictly followed my instructions yet, so I suggest please make sure you use the shadcn UI components. Don't create a custom component unless it's necessary. Use the shadcn UI libraries throughout the project wherever it's possible. I will also update our UI prompt to be more specific for the future projects. Now, the AI coding agent actually understands my requirements. It starts refining the interface and asks me to initiate the shadcn UI. I clicked yes to proceed and it installs a bunch of components from shadcn UI. There are just a few options to click through. Once these base components are installed and included in the codebase, I can guarantee the UI will look much more polished than the first draft. It doesn't take much time. After a few minutes, you will see a much more refined version. If a human did this, it will probably take days to reach this stage. But with AI, you can vibe code and finish in a few minutes. I will speed up the playback here. As you can see, it's updating our components with shadcn UI. I will skip through the process and show you the actual product. Cool, so after a few minutes, you will see we've reached the end of the second step. The AI will pop up a code commit. Let's commit the code before we go and refresh the dev server to check out the UI update. As you can see now, it's based on the shadcn UI components library, and it looks much more polished than the first draft. After just a few prompts, most of the main components are ready to go. On the left-hand side is the LLM chat panel. On the right-hand side is the MCP control panel. You got the light and dark mode toggle. You can click on different service tabs to switch between Jira, Confluence, GitHub, Slack, and some other cloud services. These are mostly just placeholders for now. You've got server configuration and the available actions panel, interface panel, etc. Most of the key components are here now. Cool. After a few vibe coding iterations on the UI, we should be in a reasonable good position to start the backend logic. Now, let's implement the MCP logic to make this MCP Client app work from end to end. We will instruct the Copilot agent to read the architecture doc we created earlier and ask it to plan out the implementation and no coding just yet. The Copilot agent starts by reading architecture.prompt.md file. It also checks the PRD document to understand the overall requirements and objectives, and reviews the type definitions as a good starting point to see what's going on. It reads the actions and utilities directory and come up with a detailed implementation plan. First, it lists out the server-side MCP actions we need for the MCP operations. Next, we have the client-side storage and MCP utilities. The storage utilities handle local storage management for saving the MCP server configurations and tool selections on the client side. Each time you make an MCP call, you don't want to re-enter the server configurations. Hence, the local storage is a good place to store these and along with tool selections. The MCP client hooks, these are React hooks that wrap the server actions. If you are not familiar with the client-side hook wrapping the server-side actions, don't worry too much. I will explain this in a diagram. For now, let's just go through the whole implementation plan first. Okay, next is the AI chat integration, which is also a server-side action. This handles model selection, tool registration, and all the LLM integrations via the Vercel AI SDK. We also need a custom chat hook to manage communications between client-side component and the server-side actions. And there's a tool registry and selection utilities, which handle tool selection and decide what tools to load for each MCP call. Here's an example of the asynchronous function for implementing an MCP operation, along with some type definitions. Now, that's the suggested order of implementation. Copilot recommends starting with the storage utility functions, since they are independent of all the other steps. A good decision. Next, it moves on to creating the server-side actions, which is also reasonable. After those are set up, it will complete the client-side hooks. Then it handles the tool registry, dynamic tool loading, and selection management. It leaves the chat integration for last, so the chat providers, chat actions, and the custom chat hooks are done at the end. If you are not familiar with the client-side hooks, let's break down how they help us trigger MCP tool calls and interact with the server-side actions. Suppose you have an execute button in your UI for the MCP tool called Get Me on GitHub. When you click this button, here's what happens. At the button click, the button triggers the execute tool function, which is exposed by use tool execution hook. The hook has a few responsibilities. Firstly, it loads the server's configuration, like the URL or the bearer token from local storage, using a utility function in storage.ts. It also manages the execution state. When it's running, finished, errored, and also appending the results that we will receive from the server action. It clears the previous result before starting a new execution. Once the config is loaded, the hook will call the asynchronous function at the server side, named the call MCP tool. This is the actual function that performs the MCP operation by connecting to the remote MCP server and executing the tool. When the server returns a result, the hook updates its state with the result. It also updates the user parameters, timestamps, status, and any error messages. The UI then displays the execution result to the user. So the hook acts as a bridge. It manages the local states, loads the configs from the local storage, triggers the server-side actions, and update the UI with results. All the heavy lifting connecting to the remote MCP server and running the tool actually happens at the server side, while the hook keeps your UI reactive and up to date. So let's kick off the first step, which is building the storage utility functions. This is a relatively standard textbook implementation, so AI can actually do this with ease. It only takes a couple of minutes, so let's commit our code at each step. One strategy I want to share for AI augmented programming is to commit code as frequently as possible. Just in case you need to revert any changes made by AI, you can use Copilot to do a no-code commit for you, but I usually just write the commit message myself. One reason is to save the token usage. If you get AI to write a commit for you, it counts as one API request to the Claude model. The premium model's consumption isn't unlimited with Copilot. So if you can do it with a one-line message, just do it yourself. Now, the second step is to implement the server-side actions for the MCP client to server connection. Anthropic already provides standard templates and code snippets on the main MCP documentation side. You can just click on the tab on the left called For Client Developers. There you will find a full Node.js code snippet showing how the MCP client server connection script works. It's a standard stateless client server connection script. You can tell the Copilot agent to refer to the reference doc to understand how the client connections work, and just paste in the URL of the documentation page. Since the Copilot has internet access, it will ask for permission to fetch the web page, and we can just click on OK. It will check if the MCP SDK is installed based on our package.json, and once confirmed, it started writing the actual server-side actions based on the example snippets from Anthropic. One thing to point out, when Copilot initially wrote the server-side action script, it used the deprecated SSE server send events transport for remote server connections. This has recently been deprecated, and Anthropic now recommends using streamable HTTP connections for remote server-to-client connections. This change happened only a couple of months ago, so the training data of Claude might not cover it. That's where humans need to step in and review or change any architectural decisions made by AI. This is a good example of that scenario. When it comes to textbook implementation, AI can do them at scale where there's no human can possibly match. But when there are updates not included in the training data, we as humans still need to review and make those decisions. Otherwise, AI might make a mess or continue with outdated code, which later becomes a tech debt in production. So I stepped in and asked the AI to look for streamable HTTP transport in the SDK and swap it for SSE. After a quick search, Copilot found a streamable HTTP transport and replaced the original SSE implementation. One thing it didn't do well was forgetting to delete the import for SSE, and there were a couple of examples I had to tidy up myself. But overall, it did a good job. It implemented the server-side actions with no other problems. Let's commit our code again. I will just write a manual commit message to save our token consumption. Now, the third step is to implement the client-side hooks. As I explained in the last section, this is another textbook implementation, and AI was able to do it with ease. It implemented the 6 React custom user hooks in just a few minutes, very efficient for standard implementation. We can commit our code again for the client-side hooks, and that marks the 3 steps, already half done with our backend implementation. The whole process took just about 30 minutes. Since now we've got the MCP control panel working and implemented the server-side actions in client-side hooks for the MCP connection, the last bit is the AI chat. I started a new chat with the Copilot. You can continue with the previous chat, but the problem is Claude Sonnet has a context window limit of 200k tokens. So if you continue in a previous chat, that means every time it's about to reach the context window limit, it starts summarizing the conversation. And I normally find that's when the response quality starts dropping. So we start a new chat. Tell Copilot to read the architecture document again. We will ask the Copilot to do a plan for the implementation of the AI chat. Again, it's reading the architecture.prompt.md file and also checking on the previous work we've done. It's figuring out the implementation details. The only correction I was instructing Copilot was to not use AWS SDK or the Google Generative AI SDK for Gemini. Instead, I wanted to use the AI SDK from Vercel. Vercel provides a few wrappers for those original AWS or Google AI SDKs. The main reason is we use the Vercel AI SDK throughout the project. It also has a pretty good integration for the client-side hooks, so we might as well just keep it consistent. There's nothing wrong with using the original AWS or Google AI SDKs. It just means we need to do a lot of boilerplate code ourselves. So that's the instruction I gave to Copilot, and it was able to understand and updated its implementation plan to suit. Cool, let's get Copilot to implement it. First step is installing the dependency packages. Then it started creating the chat provider and also the tool registry for the AI SDK integration. Then it's creating the permission system. Everything is going as planned. It also implemented the custom use chat hook. So yeah, as you can see, NetSnet UI we developed so far. You can select the tools you want to use on the right hand side. Before we can get the AI chat working, we need to grab the credentials from AWS or GCP. For demonstration purposes, I will just quickly grab the API key from Google AI Studio. If it's AWS Bedrock, you will need to grab the access key ID and the secret access key to have the agents on Bedrock working. For Google, you just need an API key. So grab the API key from your account and put it into the .env file in your local for now. Let's quickly send a message to the AI chat and see if we can get any response. It doesn't look like we got the response yet, so let's just check with the Copilot what's going on, and Copilot was able to diagnose the issue. We actually saw an error in the response payload, and that's actually to do with the formatting of the tools that we are appending to the Vercel AI SDK calls. It took a few iterations to fix this, but once it's fixed, we were able to fire a MCP chat and get the response back on the chat panel. At this stage, we are pretty much completed with the MCP client. Let me just spend a few minutes to explain to you how the AI chat actually works under the hood. The main chat UI is implemented in a component called the chat panel. Users interact with the chat panel to send prompts and see responses. The core element of the chat panel is a React use hook called useChat. UseChat is a custom hook, however, it's built on top of the existing Vercel AI SDK useChat, plus our custom MCP tool integrations. So the useChat hook does the following. It manages the chat messages at the client side, adjusts the inputs, updates the input state loading, triggers the tool calls, and handles the permission requests. And we mentioned about the user tool registry in the MCP session. The hook listens to the tool changes and updates the AI SDK tool list accordingly. Tool selection is managed in local storage and updated in real time using custom events. When a user sends a message, useChat calls an API endpoint called API/chat, which will have a prompt, selected model ID, and a list of the enabled MCP tools that we want to include in this particular conversation. The API route validates the model, converts the message and tools metadata to be compatible with Vercel AI SDK, and streams the response from the AI provider, which is Gemini in this scenario. It's important to know tools are sent as metadata only. The actual execution is handled at the client side. So if AI decides to use a tool, the Vercel AI SDK triggers a callback function included in useChat hook called onToolCall. When this callback function is triggered, it brings the tool call parameters that returned by the Gemini AI and use them to trigger a server-side async function called execute chat tool. This function handles the actual execution of the tool call and connect to the MCP server. That wraps up the full cycle of the AI chat integration. There is plenty more to explore and deep dive into, but this covers the essentials. I will drop the GitHub repo link below, feel free to check it out. And don't hesitate to leave any questions in the comments. I'm always happy to help.